Hello, Professor Sardi here with you again. We're going to take a look at a question that would seem to be from calculus, but that could be deceptive. All right, so here's our question, and I'm going to follow this up with a diagram. Because we are dealing with these poles being perpendicular to flat ground, then we have right angles here and here. A and B will both have to be greater than 0, because if they're not, then we don't have any poles. In the diagram, I have A greater than B. We don't know if that's necessary, though. You could have A equal to B. You could have A less than B. We don't know yet. C, the distance between the bases of the two poles. That will have to be greater than 0. Because if it's not, then you have no space between the two poles. The two poles are the same, and there's no place for them to meet. The distance from the base of the height with pole A to where the wires meet is x, and so what's left over, c minus x, is the distance from its base to the meeting points. Because we are dealing with right angles and therefore right triangles on the left and on the right, I've applied the Pythagorean theorem. The square root of a squared plus x squared, that is the length of the hypotenuse of the triangle on the left. It is also the portion of the wire that goes from the top of the pole with height A to the meeting point on the ground. And so similarly, this is the length of this portion. And we want to minimize the total length of the wire used. This function is dependent on x. What that total length will be continuous. Notice that a squared plus x squared and b squared plus c minus x, that quantity squared. These will be greater than 0 because although x could be 0, we could have the wire going directly from the bottom of the pole with height A to the top of the pole with height B, or vice versa. We could have this so that x could be between 0 and c inclusive. X squared and c minus x quantity squared, those are going to be non-negative, added to strictly positive values, a squared and b squared. So what's underneath both those square roots will be strictly positive, and this function will be continuous. This function will be continuous on the closed interval from 0 to c. We could apply the properties of limits where we first split the limit across the sum. Then, since the square root is dealing with strictly positives underneath, then we can bring the limits inside. Then again, split up the sums inside. The limit of a constant is a constant, as we see here. The limit of a power is the power of a limit. And then that final part on the second square root, we would have brought in inside of the squaring the limit of c minus x. Again, split the limit across c minus x, and the limit of a constant is a constant. Without showing all of the details, the limits would exist. And not only that, as I mentioned, along that closed interval from 0 to c, the function would be defined everywhere within that. The limit would exist everywhere within that. And the limit as x approaches some value within 0 to c would equal the value of the function that x is approaching. Now, because I'm talking about the function being continuous on 0 to c, what I'm hoping to apply is the extreme value theorem.